Right, confirming you'll see on the screen, right? You'll see in the elevator.
Yeah.
Right. So we know an electromagnetic machine. You have the electrical system, and the electrical system going to interface with the magnetic system, and then the magnetic system going to interface with the mechanical system, which is how most machines work, right? They use a magnetic field to turn a shaft, or in this case, you're using a magnetic field to pull an object towards you and to push it away, to lift it or to lower it. So the electric system is basically voltage giving you the current, the magnetic system giving you the MMF, flux, magnetic field, and then that magnetic field, however, if it's a motor or a generator, a vertical lift contactor, it will then interface with the mechanical system and you will get turning however you want. So it's electric, magnetic, and mechanical, right? So the three. And then energy conversion, the electrical energy from the source is equal to the mechanical energy to the load, the increase in the field energy, and plus the energy converted to it. So remember, you have energy, you need to use some of that energy to generate the magnetic field. And once that magnetic field is generated, it would then use some of the energy to use the mechanical load, to do the mechanical load. And in all things, you have losses, which is the energy converted to heat, because you will have I squared R losses, right? So the electrical energy from the source is the total energy supplied to the system. So from a battery or whatever, right? The mechanical energy to the load is a useful output energy, like rotating the shaft and lifting the load. So that the mechanical part. The increase in the field energy is the energy stored in the magnetic field. So remember, anytime you have something that works through a magnetic field, you need to use energy to generate the magnetic field. It doesn't happen instantaneously, or it's not separate. You actually need to use energy to set it up. Alright? It's like opening a business. You need to have money to start the business. You can't make money from nothing. Yeah? So the magnetic field is what will allow you to do the mechanical work. Yeah? Our energy converted to heat, energy loss, resistance, I squared R, eddy currents, and we have hysteresis losses. Right? So it is not useful, obviously, and it dissipates it as heat. Cool. No, so you get into the vertical lift contactor. So based on the operation of it, I'm gonna get my laser pointer. So going through it. So I started from here, right? So you have a battery. This battery gonna give you a current through the resistance, which modeling the resistance to the coil. So when you have this resistance going through the coil, you have a magnetic field being generated. And when you have this magnetic field being generated in the magnetic circuit now, so that MMF gonna give you a flux, also, and the flux gonna emanate out in this direction. So we did the right hand grip rule, so we know the direction it will go in. So when it goes, it splits. Most of the time, the two end pieces will be half because you want it to be symmetrical. Reason being, if one side stronger than the other side, the thing it lifting up will kind of lift up slanted. Because remember, one side stronger than the other side, so it will be kind of slanted when you're lifting it up. So you don't want that. So you want the attraction on three of the end pieces or the attractive pieces to be the same. So the material will go up uniformly. So basically, a horseshoe magnet, you can think of it. So you have this endpoint here, this endpoint here, and this endpoint here. So this here is our stator, it's fixed. So this magnetic field going through. So this endpoint here, it will have a magnetic field being generated. Yeah, and when that magnetic field cut this armature, so this part here it's free to move, like it's literally free to move. It will move, right? So, and we did this in, well, the first piece when I was going through the magnet and the coil with Cyril and Vernon is the same concept here. So when you have this magnetic field being generated on these three end pieces, you have a north, south, and a north initially. When it starts to pull away, this will then generate something to attract it. It's literally just a magnet. It's just a magnet. When you have a magnet and an old iron, when you put the magnet close to the old iron, and it'll just be attracted to the iron and will stick on your fridge, then plug and thing on your fridge. It have a magnet at the back. When you put the magnet close to the fridge, it'll stick on the fridge. Also, it's the same concept. You're just using an electromagnet to make this magnetic part here, and when that magnetizes, it will just attract this piece upwards. That's all. That's what they call it, a vertical lift contactor. And well, obviously, if you keep lifting it up, it will reach a point where they touch. So it basically at its up position. Alright, so we read here. When the switch is closed, a current flows through the coil. Yes. And sets up the magnetic field in the seal core. First thing. The magnetic field induces a magnetic field in the movable steel armature, which is just going through the operation. So this north pole will induce a south pole, this south pole will induce a north pole, and this north pole will then induce a south pole. Yeah. So the induced field is set up in such that there is an attractive force, because you don't want to push it away now, because it's a vertical lift. You want to lift it up, so you have to induce a attractive force, right? And that pulls the armature towards the fixed steel core, which is this here. Yes, so you're basically pulling it up, and well, basically movement of the machine, right? So far, voltage, current, coil, flux. When you have the flux in the fixed steel core, it will induce an attractive force that will pull the armature towards the fixed steel core. And that basically does it. And yes, this is a magnetic circuit. So if you look at the core or the flux part, it go in here, it's splitting left, right, going through here, going through our air gap, and it coming around. So it's still a magnetic circuit. It just have an air gap in it. Yeah. So the air gap will be part of the flux part. So cool. So everybody good here? You need me to explain anything else? Because there's the backbone and everything else that we're gonna go through. So you all good here? No questions, right? Cool. So
I can ask one thing quick.
okay now.
You remember when you do the quotient rule and get minus? That is why I take the modulus because it's opposite attract to pull it in.
Right.
And that is why I take the modulus.
The modulus is telling you the magnitude of this triangle. They're not really
Yeah.
saying the direction. If you say the
So
modulus
if it
of
was
anything, it's just telling you magnitude. Yeah. So
I
yeah.
thought once it's minus, I mean it pushing it away.
It could, but if you do the modulus of it, it will remove the sign. So that would
Yeah,
be
it'll be
positive.
positive. Say pull.
Yeah, well, if you do the modulus of something, you will not have the sign. Because the modulus of any number is positive. So if you want to know the direction, you can't use the modulus. Because the modulus will just give you the
Okay.
magnitude of it. Yeah?
Yeah.
So without the modulus, yes, a negative means you're basically supplying energy, and then a positive means you're gaining energy. Yeah, so
Thanks.
attraction, if you're attracting something, you're gaining. If you're, if you're repelling, you're losing, and if you're attracting, you're gaining. Yeah, because to repel something, you kind of have to push out energy. If you're receiving something, you're gaining energy. So like that, right? So cool. So the first equation, so with the applied voltage, the current flows through the coil. We know this. And it establishes a field in the core. We know this. The field will attract the movable armature upwards, thereby producing a change in flux linkage. So let me just use my pen. So remember, flux linkage is basically the amount of flux lines passing through the material. That's basically all it is. So this armature at the bottom here, and you have the horseshoe, just piece of it, otherwise you do the whole thing. So you have this, right? You have the egg up here. So we know this north, south, north, south. So we know this going to induce a flux. So let's say there's four lines on both sides. One, two, three, four, right? So initially you have a big air gap, obviously. So the amount of flux linking with this north pole and the south pole here for each end, the amount of flux linking or cutting will be low because the air gap will be at its largest value, right? But as this contact start to move upwards, the air gap will reduce. And when the air gap reduce, due to Faraday's law, anytime you have a magnetic field cutting a conductor, which is the north and the south here, it will induce a EMF. Yeah? And that EMF will be in such a way to oppose. But we'll get to the oppose part just now. But just know this magnetic field that was induced by this magnetic field from the coil will then cut here, and because of that cutting, he will induce a EMF. So you have two V. So you have V coming from here, which is a V in this coil, and then when this end, with these ends, induce a magnetic field in the armature, this will also create a magnetic field, and when it starts to move, when you have flux lines cutting a conductor, he will induce a EMF in this here. And due to Faraday's law, it will be plus. Because Lenz's law states that this E will work to oppose the change that causes it. It will not want to aid it. So because this cutting this conductor here, it will actually produce a minus E. Or the E will actually oppose this V because it want to reduce the flux change. Yeah, remember, Faraday's law states that the EMF will be induced, and Lenz states that, okay, I will want to oppose the change that you're trying to cause on me. Right, but we'll get to this just now. So, the induced EMF from the magnetic field is basically caused by the change in flux linkage per unit time. So, basically, change in flux linkage will basically give you the induced EMF. So the faster you change the flux, the higher the induced EMF. Okay? That's basically the first piece. And then, well, consider differential time, whatever the case is. So this V now will basically be R by I plus E. So you're getting to this just now. The differential energy transferred from the source to the field minus the resistance losses will basically give you this. So again, to that now. Cool. So we have this. So the power supplied by the force, remember power P is VI, right? And from before, we had V is equal to Ri plus E. So basically, if you multiply that by I, so you get this, you get I squared by V. So this first piece here, it will be Ri squared, and this will be E by I, and this side will be V by I. So remember, it's V IR plus E. So if you multiply everything here by I, you get I squared R plus E. And then, if you differentiate with respect to time, let's just add a dt at the end of it. The energy supplied, which is dWe, if you factorize the R on V and the I, you basically end up with this here, which is just EI dt, because this side here, it will stay. And you carry this on this side, you factorize out the I dt, and you end up with this. All this basically saying is that some of the energy which is applied to the field is stored in the field, and at the same time some of it's converted to mechanical energy. So the total energy you have when it's applied to the contactor, some will be stored in the magnetic field. We went through this before, the first one. So the energy, some stored in the magnetic field, and then some of it will actually go to do the mechanical work, which is lifting up the contactor. Yeah. And then from friction and windage and stuff. So this is the first one. Total energy is equal to the energy stored in the field plus the core losses plus the energy converted to the mechanical form, and then plus friction element, which is just is metal on metal, so we will have friction. Cool. You don't need to know majority stuff here, they're just an issue. And well, this one is the same there, right? So from before, every armature is fixed, so it cannot move. So right now in this case, you basically bolt this down. So the armature cannot move. So if the armature cannot move, therefore the change in flux linkage will be zero because it's not moving. Yeah, so the dWm, which remember that is the mechanical work, will be zero because it's not moving, right? So all the energy will just go to the field. So the dWe will just equal to dWf. Because the Wm here, this is basically just zero. Because you're not doing any work, it's not moving. Yeah, and that's basically what this trying to say. So if a question come and asks you, okay, how will the total energies change if the movable armature is fixed to the ground? You'll basically, first thing you'll tell them is the equation, and then you'll say, okay, if it's not moving, the lambda, the flux linkage not changing. So therefore it's not doing any work. So therefore the Wm, which is the mechanical work done, is zero. So therefore the total energy will just go straight to the field. Yeah, that is that piece. Cool. So now we get into this stuff. So if you ignore eddy currents or core losses and stuff, just to keep it simple, the BH curve becomes a single value curve passing through the region. The electrical energy supplied is stored in the field. So just like how we have a graph, if you have from point A to point B here, from the forces, this is basically the energy stored in the field. Because you're going from one flux linkage point to the next. Because remember, when you move the conductor, the flux linkage gonna change. Yeah, because remember, there's a magnet literally moving up. So if you move closer to the core material, the amount of flux lines passing through will increase. And if that increase, the energy stored in the magnetic field will also increase. Okay, so you actually need a little bit of energy. So if a tiny increase in the flux linkage, it will need a small amount of energy. Because in order to change the flux linkage, you actually have to move the armature. Alright, and takeaway from this slide is the field energy is basically integral from 0 to lambda, which is here, straight up to here, which is basically moving the armature from the bottom straight up to the top and a touch. That is the total energy stored in the field. So 0 to lambda by I by the lambda. Because this is the y-axis, because our lambda I curve, and you're integrating on the y-axis. So you're actually finding the area bounded on the y-axis. So this whole area here is basically you going from bottom straight up to the top. So if they ask you to go from one flux linkage point to the next flux linkage point, you will need a little bit of energy. Yeah, at least what this is the main one. And this here. Alright, cool. So takeaways from this side. So this is where the takeaway. So the energy added is the magnetic force, which is F, by the change in flux, which makes sense. So as the flux change, the energy added will basically increase, right? And this one is the big one. So this is the one you have to remember. So as current increases, the flux will increase. And if the flux increases, the energy stored will also increase. That's basically how it does work, right? And everything else is kind of, well, have a little thing at the bottom here. So the current is how hard you're pumping. It's like you're filling a tank. The flux linkage is basically how full the tank is. And the area under the curve is basically the total energy stored in the tank. Because you're just integrating on the y-axis. So this whole thing here is the tank. If you need to go from one level in the tank to our next level in the tank, aka going from one position of the armature to the next position of the armature, you will need a little bit of energy to do that. Basically, trying to say. Right, cool. So, building up to it. So, obviously, the vertical lift contactor, it have a air gap in it, right? So, we went through this with the BH curve, but the presence of the air gap tends to dominate the reluctance characteristics of the flux path. Right, so yeah, somebody asked me a question. Okay, cool. Similarly, the air gap dominates the BH characteristic because we know if what have a large reluctance, free space. The BH curve for basically free space is a straight line, or non-ferromatic material is basically a straight line. Yeah. So the air dominates because the permeability is extremely low, we know this, compared to iron, making its reluctance so large that it governs the flux flow and forces the overall magnetic response to behave like in a straight line. Okay, so I have this, and this basically derivation of the cut. So there's a straight line here. And the equation I want you all to remember from this, you don't need to know the derivation because you don't need to know proofs. So this is it. So the energy stored in the field, so you have two ones. You have lambda I on 2, and then you have F squared on 2R. Remember, this R is reluctance, right? Not resistance. Same concept. Nice. So let's get into this stuff. So moving slow. So assuming the armature, the vertical lift contactor can move between two finite non-zero air gap distances. Remember, when you move the armature, you're just changing the size of the air gap. That's really all they're doing, right? So each of them will have a different straight line. So what these straight lines are, when you look at the graph itself, there's a one of the lines representing the down position, and then the other one representing the up position. That will show what it is. Yeah, one down, one up. In between here, you could have multiple different lines. That is up, up, maximum up, and there's basically lowest you could go. Anywhere in between, you could change. But here the base just give you the total, which is the maximum, going from down straight up. So, so the first thing, the armature is held down in the down position. When the switch is closed, so the moment you close the switch, remember, the circuit itself, you have a switch here. Remember, you want to control when to move the armature. So in most operations for you all, when you close the switch, the armature will just go straight up. You all will not worry about controlling the like how high it go up and all that. When I close the switch, it will just go up like a relay. Yeah? Cool. So the current in the coil rises to the steady state of Vt and R. So at this point here, your flux linkage is zero and your current is basically zero. The moment you put on the switch, we know the current will increase. And if you go through this, if the current increase, we know the intensity will increase and it will go through the circuit. And when you induce the EMF, your flux linkage will also increase steadily. Because if you increase current, you will be increasing your intensity. And remember, your flux linkage is basically how the magnetic flux lines cut in the core. Right? So if you increase the current, you're basically going to be increasing the flux cutting or linking. So that will just keep increasing up to E. So there's your starting point right here. So the current, it rises steadily, not instantaneously, to Vt and R. And this is indicated by A here. The current does not jump instantly to V and R. And the flux linkage builds with the current, which is what I said there. Right? So where I can start here. I can start here. So this I, if you increase I, you will be increasing your flux linkage. Yeah, that's basically what I'm telling you. And same with the flux. And if you increase the flux linkage, your flux will also increase. That's basically what all this generated for the equation that I use. So basically current leads to flux increase and the flux linkage will increase. So if you increase the current, you increase the flux, and if you increase the flux, the amount of flux linking will increase. Yeah, which is why the graph goes up because there's that direct proportional relationship between I and lambda. Yeah, cool. So this is setup understanding, right? So stage one, initially energizing, the current rises slowly, the flux linkage increases, and it won't have any movement as yet. All this is setup. The movements is between this here. So this is the movement part, or this, or this. Up to A is just a setup. Because it doesn't instantaneously jump up to VTNR. It slowly works up to it. And then two, the armature starts moving. So what happens is the air gap decreases. We know that because it's moving up, right? If the air gap decreases, the reluctance will decrease. Which, because remember, if you have less air, the reluctance will be less. Yeah? So the smaller the air gap, the less the reluctance. And if you decrease the reluctance, the flux will increase faster. Because you know from before, current giving you more flux and more flux giving you more flux linkage. So, which is why the flux increases faster. Yeah. And then extra induced EMF appears. So this is an important point. We'll get to this just now. This actually slows the current rise. So this basically Faraday's and Lenz's law, right? So from before, when you induce a magnetic field in the armature and it start to move, that induced magnetic field cuts in the core of the stator or the fixed core, right? When that cutting happens, it will induce a EMF, and that EMF will work in such a way to oppose the change that caused it. And the thing that opposed or set up that magnetic field was V. Yeah? So let's keep this in mind for now. And the last stage, it will just keep moving until the armature is fully pulled in. So when that happens, the movement stops, obviously. The flux becomes constant because remember, it's basically just a core material now. It has no more air gap. And the induced EMF goes to zero. Because remember, this induced EMF is due to the change. Remember, Faraday's law says the change in flux. So if you have no relative motion, you won't have any induced EMF. To induce something, you have to move. If you're not moving, you're not inducing, right? So when the armature reaches the fully closed position, or when it reaches the top, it won't have any more motion to go. So the flux linkage not going to change. And if the flux linkage change, the induced EMF will change because E is d lambda on T. So if this falls to zero, the induced EMF will also fall to zero. Right? So at that point, the current finally settles to V and R, and the flux linkage reaches its final steady value. So what that means on the graph itself, so you here now, wonder where to have the, okay, I'm gonna go through this and I'll go back. So as the current, the flux increases of the lambda, since, oh, I'll make this change. That's not what to do. So the increase in the EMF causes, in the coil, causes the current to reduce. What I mean by that is this here. So you have VT, and we know when you have the induced EMF, it will oppose that same E, and then obviously it divided over R, which is I. So what this means is, initially as the armature start to move, and the flux linkage will gradually start to increase, while that start to change, it will induce E. And as it continue to move and move and move, the value of E will basically keep increasing and increasing and increasing. And if E start to increase, because the flux linkage increasing, if your flux linkage increase, the induced EMF will also increase, because E is the lambda and T. So if the change in lambda and T increase, obviously the E will increase. But if E increase now, Vt minus E, this overall value here, will actually decrease. So if Vt minus E decrease, when you divide that by R, the current itself will also decrease. So from here, this is Vt and R, which is I. So it's the starting current, right? So now we know two things. We know as the armature start to move, we know the flux linkage, which is the y-axis, We know that will increase. We know that. But also, while the lambda increasing, the currents will start to decrease. Why this equation? Because E is caused by the change, which is Lenz's law. But it will try to oppose. So basically what happens is one trying to increase the flux linkage and then one trying to reduce the change that causing it, which is why it's not going this way, it's going this way. Because you're trying to reduce it. So that will keep happening, it will keep reducing, it will keep reducing. And when it reaches this piece here, that represents it basically reach the top. So it contact. It has no more movement to happen. So when it reach there, that basically when you're gonna have a maximum amount of flux linkage. Because think about it. So now where I drew that. Right, so these lines here, when they reach the top, the basically is gonna have one core material. And all the flux line basically gonna be cutting the material. So basically gonna have a maximum amount of flux linkage when it reach the top. So it have no space to prevent. Everything cutting. That is at the top of the contactor. There was I. Here. So at the top it stop. So you have your maximum amount of flux linkage, that your maximum value. But also Vt minus E now. At that point when you reach the top, the E will drop to zero because you have no more change in flux linkage because it reached the maximum value. So if E goes to zero, Vt and R, it goes back to I. So if you're here now, how you gonna reach back to I? You have to go back down to here. And I basically how it does work. So that's our first piece. So you're basically going like this, up, and you come back down. You're just gonna be repeating over and over. So Vt and R, then as it start to move, it will be Vt minus E and R. And as that continue to decrease, the flux will increase because of the motion. Then they go up to P. And when it reach the top, since it have no more change in flux, the E will drop to zero. So you can end up back to Vt and R. And it'll go back down. Remember, nothing um is instantaneous. It always have a little change or time delay. So it's not instantaneous. Cool? Sound good?
Question.
Yeah, go ahead.
So at A it will be VT over R,
Right.
and at P is there will be E will be in the equation, you said? With VT minus E over R.
Right. So P, this value of P is representing a maximum flux linkage point, right? But this
Okay, good.
value of P here is at a different value of I. What this I represents, so we can say, I want to say I min is equal to Vt minus E max. Because this point P happens when the flux linkage is at its maximum, no? So if the flux
Yeah.
linkage at that point is at its maximum, the maximum induced EMF will happen at that point, right? And basically, if you divide that by R, you get the current. So this will basically be a one is not max, but is the minimum. Because the current decreasing while the flux linkage increasing. So at this point
I
here,
said it'll be going from A
mhm,
to B over and over.
yeah, correct. So when you reach here now, at the point it reach there, after a small time, remember you have no more change because the magnetic field not changing anymore. So if the magnetic field not changing in terms of the linkage, the induced EMF will go to zero now. So, and if the induced EMF go to zero, you're gonna end up with Vt and R. And if you end up back to Vt and R, you have to go back to E. So this the E not instantaneously gonna go back to zero. It will just reduce. Yeah.
Yeah.
So you're going to 0 to A, then it start. So this portion here is when it's actually moving. Yeah. So
And
when it
that's
reach
just VT minus E for over
correct.
R.
So this this piece here is the Vt minus E and R in terms of the current. Yeah, the flux linkage is due to this here. We have an equation that you could use to go from lambda back to I back to lambda, which is this here. So if you know what the current is, you will know what the inductance of the coil is. So you will get the flux linkage. Yeah, but really and truly, when you start to move, the flux linkage will gradually start to increase. And the flux linkage gradually increasing, the induced EMF will increase. But as the induced EMF increases, because our lens is low, that will oppose. So because it's opposed, it will end up being Vt minus E and R. So when the flux linkage start to increase, the current will start to decrease. And that's actually a safety feature because you will not want the current to be increasing while the flux linkage increasing because your system could overheat. Yeah, so cool. Right, so we went through this already. So since the movement of the armature ceases at the top, the change in reluctance ceases. So remember, when I reach the top, the reluctance is not changing anymore, right? Because it reached the top. So the change in flux and the flux linkage ceases. The induced EMF falls to zero. The coil returns to Vt and R, but for lower reluctance R, the MMF will be this. So basically, at the new circuit, the MMF will change. But the main point is this and this. Yeah? Because remember, when it reaches top, you have no more air gap. So if you have no more air gap, the total reluctance will decrease. Yeah? So now, if phi is equal to F on R, at the top, when it contact, right, the reluctance will basically be at its lowest value. So if the reluctance at its lowest value, the flux will technically be at its highest value, which is why this here is the maximum point. Cool. So this line here represents when it's at the down position, and this represents the up position. And just like before, you basically have one, two, three, like basically this extended line is when you start to go into the different type of operations. But it's basically 0 A P back to 0. And yes, the area bounded by that is the mechanical work done to move it from the down position to the up position, right? WM is mechanical work plus your losses. So you good there, right? So this is what has happened at the top. So the question asks, what happens to the induced EMF or anything related when the armature is at its top position? The first thing you say, well, the change in reluctance will go to zero. The change in the flux and the flux linkage will cease. Okay, you have no more relative motion. The induced EMF falls to zero. The core returns to Vt and R, but it will be for a lower value reluctance because you have no more air gap anymore. It's just core material. Right, cool. So now we're going into the operations. The operations are real simple. Right? The first one is your constant current operation. So for constant current operation, remember you here right now, right? This is where you're starting from. There's always the start. So you have three possible ways you could go. You could go up here, which is just narrowly just a I'll say normal operation. So as you increase the flux linkage, the current will decrease, sorry, and it will go to P. So that's the first one. The second way I could go is a constant current. What that means is from here, while the flux linkage keep increasing, the current actually stay in the same value. So instead of the current decreasing while the flux linkage increase, both of them stay in constant. So one increasing and the I stay in the same value, which is why they say the constant current operation. So to have that, if you think about it, go back to principles, the E comes from the change in flux with respect to time. So the change in flux linkage with respect to time. So if I was to move the armature real slow, which means that that flux linkage, the change in flux linkage is approximately zero. Like it's gonna be so small that you're not gonna have any great change or any great change in the induced EMF, right? So if this small, if you move it real slow, this gonna be approximately zero. Approximately, right? Nothing in life is perfect. So if this is approximately zero because you're moving this real slow, like real slow, this would drop off. So a very slow movement of the armature results in a very small and negligible generation of EMF, right? So you could approximate it to be zero. Hence, the current remains virtually constant. We know it's not really like perfect, but we know we could say it's a straight line, right? At the value I. And the movement happens from A up to B, which is a constant current operation. So any constant current operation, the current is constant and your flux linkage will increase from the initial value up to a maximum value. Yeah, that's what I mean by constant current operation. And just like before, if it's moving slowly, this B here will represent when it reach its up position. Yeah, that's moving it very slow. But it's still gonna go to the up position, but it will go to the up position by keeping the current constant. So both going up to the top, there's just one going up, and while that one go up, the current will decrease and the flux linkage will increase. Any constant current operation, the first thing you have to do is you have to move the armature very slow, which will result in a negligible change in flux linkage, which will give you a negligible generation of EMF, which means that E is approximately zero, which means that the current will just be VT and R. Right, and then well, we know up here is the opposition. So there's the opposition for your constant current operation. This here is the opposition for your normal operation. And we're going to do this one. Right, so the shape of the lambda curve from down to up of the armature depends on the speed at which the armature occurs. So the shape of it, so if you go for this one here, it's relatively fast. This one here, real slow. Because you need it to be very slow so you wouldn't have a large change in flux linkage. Yeah, so that basically constant current operation. That's what it is. Slow, small lambda, small e, Vt and r, constant I, and the flux linkage will increase because the flux linkage is due to the change, how much cutting you have. So the cutting will still happen, but just how fast the cutting happens is where you change, right? Cool. Right, so the next operation is the constant flux operation. So just like before, you're starting from A, but now the current changing for sure. But the initial flux that start off from at A is staying the same, which is why they say constant flux, right? So if you wish to keep the flux constant during the operation, the flux linkage during the operation will also remain constant. So if you look at it, if this here is what we change it, we want this to be constant. So for this to be constant, your flux had to be constant. So if this constant, this will be constant. Yeah? So, well, look at this. If this change and this change, therefore this going to change. So if this change and n is constant, the only other thing that you could change is I to compensate. Because something had to compensate. Something had to compensate. So if this increase and this increase, based on this equation here, I will have to compensate. So since the reluctance is being reduced during the operation, because it's going up, we're going in the up position, to maintain the constant flux, the MMF must be reduced since n is a constant. So what it means, right? This here is you're manipulating. So flux, so if you're going up, you're going in the up position towards the contact, you know your reluctance will decrease. So if your reluctance here decrease, you want this to be constant. So for example, let me do it with numbers. Initially, let me say phi r is equal to 10. Yeah, so it's 10. So therefore, Ni will basically be equal to 10. That is the first starting. Let me say that as at E. Now, it going up, the contact going up. So let me say at another position, let me say the reluctance half. So if the reluctance half, obviously the 10 will half, right? So now phi r is equal to 5. But remember, we have a constant. We want this to be constant, right? So if this change here in order to compensate for the entire operation, this flux on this side now, in order to get back the 5, you had to reduce the current. So you had to basically now halve the current or reduce the current. Because you can't change N, because N is the amount of turns in the coil. You can't yank out more turns. So the only thing you can do here is to reduce the current being supplied. So if you reduce I, you will get back to being 5. So by doing that, you basically have a constant current operation. So the only thing you can really manipulate here is the current, because the current comes from Vt on R. So you basically just going to be editing the terminal voltage. Yeah? So that's constant flux operation. For constant flux, the this had to be the same. The flux linkage had to be constant. And if flux linkage constant, the flux had to be constant. But if you change the reluctance to keep the same flux, you'll have to change the current. That's basically what I'm trying to say. Yeah. Cool. So some graphs. So we have, remember, the equation WE is WF plus WM. So that's how we generate it, right? So the first piece is this red piece here. So that is the field energy at the down position, which means that the armature basically at the down position, which is where it's starting from. So the energy stored will basically be you're integrating from 0 to lambda 1, and you're multiplying it by I, which will basically just be this area here. So with respect to the letters, it will basically be 0 to A to C to 0. So this whole piece here will basically be the field energy stored in its down position. Oh yeah, which is less. And then the next position now is the field energy at the up position. So which should be the blue. So that'll be 0 to B to D to 0, which is the blue, this blue triangle here. So obviously, as you go up, the energy stored in the field, you expect it to be more. Yeah, because your flux linkage is the highest. So the energy stored in the field will be its largest value. And well, initially, the energy stored in the field will be at its smallest value, right? So now, if you actually want the change in the energy stored in the field, you'll just subtract the two areas. Yeah? So that's what I did here. So if you take the red and you subtract it from the blue, you'll basically get this piece on top here. And this here will basically be WF. Yeah? Because it's basically where you start with the bigger one, subtract the smaller one will be the change in your field energy. And that's basically all that pieces. So that'll basically give you delta WF. That's how they get it. They basically subtract the energy stored in the field initially from the final or the up position. So the up energy stored in the field minus the down. Yeah, okay, cool. And well, we have Wm. Well, we know Wm now, the energy released by the field. Remember, we have We. Yeah, your Wm plus your Wf. So the mechanical work done will, in order to move it from the down position to the up position, it will basically just be the shaded region in between, which is here. So it'll be 0 to A to P, back down to 0. Alright, cool. So the total energy now. So the total energy supplied by the source to the field. So the total energy is basically energy from where it starts, which is at lambda 1, to where it end. Okay, end up here. Right, and it will basically be the whole area. So obviously this not bounded by anything, right? So it'll basically be you're starting off at A and you're going to B. So if you start off at A and you go into B, the area bounded will basically be, if you integrate between these 2 points, all this here, You're not shooting this piece because this is not covered by anything. Because A starting from here going this way, and this will be the area. So this will be a WE. Or you can say a change in WE. Yeah, and as you work down and raising the armature from the down to the up position. Yeah. This work splits into two things. You have the work and some of the energy stored in the magnetic field, and you have some of it doing the mechanical work, which is this piece here. Cool. And we're getting into the equations, well, the equations part now. So this is basically just an explanation of it, right? So if you start from A, which is at x, and you basically change the distance, or you add a small change in distance, the line itself will just move to the left. That's basically what's going on. And the energy it takes to do that will basically be this here. So the state at the position of x is represented by A prime, which is this here. So you start here, and the state at the position x plus dx is B prime, which is right here. That's how before. So you go in this way, right? And well, the differential mechanical energy dWm is associated with the movement dx. So that'll be 0 to A prime to B prime to 0, which is your mechanical work done, right? Or the change in mechanical work done. So now we consider any movement operating point along A for the segment A prime to B prime. So that basically be here to here. That area, or this whole area here, which is dn, we have an equation for it, right? Which is this here. So that area is 0 to A prime to B prime to 0, which is the mechanical work, is basically just force by distance, or the change in distance. This is the backbone of it, which is the force on the armature. Yeah, so the dWm is basically F by dx. I basically what it is. Yeah. Right, so we get into the equation. So you don't need to know the proof. So I kind of circle the important part, right? Sometimes he could ask you how the equations for both that's happened. So the first one is the constant flux equation. So in constant flux, the current decreases, but the flux stays constant. So that's why I say constant flux, right? So if you go through it, so we know there's the main equation for everything. So since lambda is constant, no EMF is induced. Remember, the change in lambda, if the change in lambda is constant, if no change happening, you're not going to get any induced EMF. Because Faraday's works with change. If nothing changing, nothing happening, right? So if that is the same, this whole thing here will basically be zero. Because you need E in order to get the work. So if, in that case, if this drop off, these two basically equate each other and you just carry this on the right, make this the subject of the formula. You always want to make this the subject of the formula. Because that way you're solving for. Wm is the force on the armature, which is F by dx. Yeah? So this will drop to 0, so you end up with this. And well, we know what dWm is, which is F by the dx, which is equal to this. So basically get this piece here. So what I'm saying is all the mechanical work is basically the energy stored in the field. And all this is proofs. First one, this here, is an important one. So if you make F the subject of the formula from here, basically end up with this. And here's where you're plugging in the different equation for D or WF. So the first equation for WF is this one. The lambda squared on 12. That's the first one. And the other one is R phi squared on 2. So all you're really doing with both equations, you don't need to know the proof. You don't need to know the proof. So this is the first one. So the first force equation at constant flux is F is equal to I squared on 2 by dl on dx. Alright, and if we use this one here, which is the WF, which is R phi squared on 2, you basically end up with this one here, which is the flux squared on 2 by dr dx. And just note this one have a negative in front of it. So you have to be careful with this one, right? So in this one, Vernon, you hardly do the modulus of it because the force can be negative. Right, and the constant currents, well, any constant currents, remember, so dWm is the area, so we know 0, A prime, V2, back down. Remember, that's going up, constant currents. Yeah, so this really to this. What I don't know is that this is what we have. The
So
dWf,
the graph?
yeah, we're going on. Which one?
No, for both of them, it asks to explain constant flux and constant
Mm-hmm.
current. Draw the graph and
Yeah,
explain the equations.
correct. So the first thing you do when you draw any graph, or when you draw any graph, it asks you to explain constant current and constant flux. You have to talk about how do they get constant current and how do you get constant flux. So the part where I explain that is here, this where they how you gonna get E to be zero, you basically make the change and the flux link is zero. And how do you make the change and flux link is zero? You move the armature very slowly. So you will talk about how we get it. So you could use these equations here. You need these two. So the main one is E is equal to d lambda and dt, which explain how the flux linkage relates to the induced EMF. Then you have this one here, which telling you the value of the current due to that EMF being induced. Remember, the EMF will oppose, right? And we just state that if you move the armature slowly, the E will approximately be zero. So you'll end up with Vt and R, which means that the current will be constant. And you just draw the graph and you show them they're going from A to B. So the flux linkage increasing, but the current also is the same value. Yeah, so that's talking about how you get the constant flux operation and then the graph. If that's to talk about the force, then you talk about the equations, right? Remember, the force in the armature is this here. So you have to read the question carefully.
Thanks.
Yeah, cool. Right, so we have this one here, and this one mentioned already. And mentioned. Cool. So here now this is where it starts. So we have this main equation from before, and we know F is dm on dx, so from before. So now dm, the only difference with the constant current, remember, for the constant flux, the dwe was zero. So any constant flux, the dwm will equal to the minus dwf. But now the dwe is not zero, it's actually a value, right? So yeah, using the whole equation, you still make dwm you substitute the formula like before. But now when you put it into the force equation, which is the dwm on dx, you'll basically have a long piece for this one, which is these here. You don't need to know the proof, but I'll just go into it. So now wf, if you look at the graph now, so you're going from this to here, up to here, and back down. But dwf now is actually from here to here and back. So if you look at it in making a rectangle, so dwf and dwm is basically, if you add them up, you're basically going to get we, because they're based just half. So that's why they said wf is equal to wm, which is just half of we. So you just replace this with this, and if you, well, you don't need to really proof, but all you have to remember is for the constant flux and the constant current operation, the force is independent of the method. So no matter which method it is, this equation here will be the same. Constant current, we only have one equation, right? Which is F is I squared on 2 dl dx. Constant flux have 2, which is the normal one, and then it have this one here, which is the phi squared on 2 dr dx. Cool, so just keep that in mind. And well, that was the end of that was it. So that went through the important equations, the graph, and how each type is generated, right? So now I'll pause it. Any questions? That's how we recording.